Hi everyone, my name is Devin Petersohn. I'm a sixth-year PhD student in the RISE lab at the University of California in Berkeley. I'm going to be giving a talk today called Scaling Interactive Data Science with Modin and Ray. First, I'd like to start with a little bit about me. I'm a retired U.S. Marine. I served in the 3rd Radio Battalion, actually, as a Korean cryptolinguist. After that, I got my bachelor's at the University of Missouri, and from there I moved to Berkeley and for my PhD and got my master's along the way. Now I'm a 6th-year PhD student. I'm advised by Anthony Joseph. I started my work in genomics, actually, and from there I kind of learned how to communicate with scientists. And, as a result of that, we kind of generalized a lot of the work that I was doing, and I helped kind of start this Dataframes effort that's going on in RISE Lab. So for this talk, I kind of want to focus on data science problems, like real problems, not like, fake problems, if you will. Data science has a scalability problem. When I say scalability problem, a lot of people are probably thinking we need more machines to handle more data, right? Data is the problem. We need to be able to scale to larger data sets. And it's tempting to think that more machines will actually solve the problem of data science scalability. But in a lot of organizations, adding more compute actually doesn't really help all that much in terms of scaling their data science efforts. Data science scalability is actually a problem in personnel. We have a system right now that's set up to where that adding more data scientists to your team actually doesn't really equate to more insights in a lot of organizations. More data scientists also doesn't mean that you have more machine learning models that are running in production. So we have this problem where it's hard enough to hire good data scientists for a lot of organizations, but beyond that, adding more data scientists isn't actually adding a lot more value to the companies that are trying to kind of build out their data science workforce. Part of that is because of the tooling, and I'll talk a little bit more about that in a minute, but a lot of organizations really look like this, where there's kind of siloed off parts of the data science and machine learning lifecycle, where we have data scientists who are working on smaller scale data on their laptop or on their workstation, and they are usually working in pandas. And then at the large scale, we have data engineers who are kind of rewriting these pipelines or productionizing the work that data scientists have done, on the small scale. And so data scientists, whenever they get a new data source or whenever they get, a new specification or new requirements, they go and they start prototyping and exploring, and then they hand it off to somebody to basically productionize it. Usually it's not the same person. Sometimes it is. We're not going to focus on that case, but often there's a handing off process. And these parts, the parts where we're transitioning from single node to multi-node, are actually a major source of friction in a data science team, right? Because if we're thinking about this machine learning lifecycle as a concurrent system, we actually have a full stop synchronization step here, where person A must gather all of their materials, and person B is blocked on person A being the data scientist, actually getting all of their materials together. And beyond this, organizations that have an actual testing environment, there's more kind of pipelining and more effort that's involved in taking this from testing to production. And so it's not just as straightforward as, create a notebook and then I can, automatically generate insights from that. It's actually very human capital intensive. The worst part about all of this is this phase where we have a rewrite when there's some feedback that comes from production. So if there's a bug or if we want to look at something else, the whole cycle has to start all over again, and we have to go through even more people or the same people again to basically get an insight or to fix a simple bug. And this is the scalability problem of data science. It causes a lot of pain for a lot of data scientists. A lot of data scientists and data engineers, for that matter, are kind of get frustrated by their jobs, because this is really, really difficult, right? Going from single node to multi-node is really hard, and there's a lot involved in actually being able to hand off that code. So data science scalability is a human scalability issue, and human time is the limit. It's not about the scalability of individual components. It's not about if only this tool could handle more data. Data actually isn't even in this equation at all. It's about being able to actually take something that was discovered or some interesting insight that the data scientists found and productionizing that. I mean, how many months does it take in your organization? So my focus, my work, has been on kind of shifting from focusing on the machine, focusing on scaling to more data. We know how to do that really well. Now can we basically take what we've learned there and focus on the user? And so our goal is to basically have tools that work for the data scientists, tools that basically enable and empower data scientists, and not really require them to be working for their tools and not add all of this extra overhead of handing things off. And so my personal work and my PhD has been in transparently scaling existing systems. The idea here is to basically abstract away all of the components of the system that data scientists don't care about and only expose the details that they do care about. We started this with pandas. Modin, if you recall, is, or if you're familiar with it anyway, it originally was a drop-in replacement for pandas, and we've kind of expanded that and generalized it, and now it does a lot more than just pandas. And so our first step towards realizing this goal of empowering data scientists and transparently scaling things involved a formalization of the Dataframe. So I worked with a lot of wonderful people in UC Berkeley. I'm very fortunate to get to work with some of the greatest minds in databases and distributed systems in the world. These folks, we all came together and we basically derived a formalism from pandas and S and R so that we could actually start to implement these things and have something that's actually grounded in formalism. So this is part of the formal definition of the data frame. I'm not going to go over it here. If you're interested, please visit the paper and read it. But the goal in showing you this is to say that we have a low level formalism that we can start to reason about when we start to when we actually want to define some operators. And so that's logically the next step, right? So we also derived a set of algebraic operators. This set of operators is it's like unique to data frames in that it contains operators from relational databases. It contains operators from matrices, and it's kind of this really interesting broad set of operators that encompasses a lot of different components from relational databases and matrices and matrix computing. And so after that, right, we have these operators. After that, we basically proved by exhaustion that we can support all of the pandas APIs. This is the first work of its kind in basically saying, instead of focusing on like, here's what we can do if we translate pandas to SQL, we took the viewpoint that what if we treated pandas API as a first-class citizen and actually tried to scale it? So now we know that this set of operators actually does cover all of pandas. And beyond that, now we need to know how to scale it, right? So we also formalized some decomposition rules, a set of decomposition rules that allows you to formalize the parallelism, actually prove the correctness of Modin. And so the interesting part about the decomposition rules is that data frames actually have operators that can be applied row-wise or cell-wise or column-wise. And it's really interesting because most systems are actually specifically designed to perform a subset of these. If it's a row store, then it can only really do row and cell-wise decomposition. And the same as if it's a column store. But we need a system that goes beyond just a row and column store. And beyond this, of course, again, we did formalization of other components of the data frame, the type system and order semantics, other types of metadata. And so now we know, the collective we, know what a data frame is formally, and we also know what operators a data frame supports, how these operators map back to pandas, so we know that we can do everything that someone would want to do in pandas. We know how to handle data frame types efficiently, and we know how to decouple the logical and physical order. So now we have all of this formalism, so we can actually start to reason about an implementation. And so Modin is that implementation. Modin is the implementation that we've grounded in this theory. So Modin, as I've said, goes beyond pandas, and it's a more general implementation of a data frame system. It's more, the underlying operators are actually more expressive than pandas. It can do more than pandas. Even though pandas has many APIs and this set of operators is very, very small, we can still do more with it because of the expressiveness. So with the design of Modin, we've designed it to be pluggable at the API layer. And this is in an effort to kind of reduce the friction, because a lot of data a lot of data engineers know SQL and they prefer to use SQL. A lot of data scientists know pandas and prefer to use pandas. And some people know a little bit of both and they don't know kind of when to use what. So we have this really interesting pluggable API where now people can interleave different cells that use different languages, and it all shares the same common execution specification that we have in Modin, that is the algebra. And all of this is kind of managed by what we're calling the Modin core. And then beyond this, we have native implementations for multiple execution environments. We have a native implementation on Ray, and we have a native implementation on Dask. No relation to Dask Dataframe. Most of our users are using Ray as their default execution engine. And so in practice, if we go back to our kind of siloed off execution, or our siloed off machine learning lifecycle, we have our laptop and workstation. Modin works great on that. Small cluster and large cluster, Modin can work across all of these. And so what we're actually seeing in practice is data scientists are able to work in pandas on their laptop and workstation. And then when they hand things off to a data engineer, that data engineer is not required to rewrite that into another language to actually run it in a production environment, in a distributed environment. They can actually take Modin, a notebook written in Modin, and run it directly on a cluster, and it doesn't require any change. And this is how we're seeing Modin get used in practice. And so one common question that we often get is, how is Modin different from X, right? Some other systems. I'm going to focus here on systems that specifically target the Pandas API. They specifically talk about the Pandas API or say that they expose the Pandas API, because we have the formalism. And I think this is really valuable to talk about, because it's really, really hard for people who are evaluating a system to know just by looking at the tagline or talking to somebody what it actually does. So if we look first at the functional evaluation of Modin versus Dask versus Koalas, accounting for duplication, meaning removing all duplicated APIs and not double counting them, Dask supports about 45%. Koalas, which is on Spark, supports about 58%, and then Modin supports about 93 and 94%. And this is total of the Pandas Dataframe API. And so starting first with Dask, Dask is a row store, and it's not able to support columnar operations, most columnar operations. It's also a little bit different from Pandas in that it sorts the data frame implicitly. This is a deviation from the data frame data model. It sorts the data frame implicitly based on the row labels or the row index. And it also doesn't have support for multi-index. It supports most relational database style queries, and it's fairly fast. And it also, but at the same time, it does require some tuning when it comes to partitioning. It's a bit more flexible in partitioning than Spark, but it's still fairly rigid in terms of how it partitions data. If we look at Koalas, Koalas is also a row store, and it cannot support columnar operations for the most part. Koalas is actually just translating to ANSI SQL, which is running on top of Spark. So in that sense, they can only support SQL style queries and UDFs and that kind of thing. And so that really kind of limits what they're able to do. They're missing support for categorical data, and the partitioning is fairly rigid. It takes quite a bit of effort to get good performance. On the Modin side, Modin supports operators on both axes, which is contrary to the other two. Right now, not everything is translated to the low-level algebra, so we don't have the full algebra. We don't have all of the operators in pandas translated down to the low-level algebra yet. And not all of those low-level algebraic operators are fully optimized. So we don't count things here where the algebraic operator is not fully optimized yet. We also don't count things here where Modin falls back to pandas. Modin is a drop-in replacement. You can use it in place of pandas. It will fall back to a pandas implementation if it's not supported. But those numbers aren't counted here just for the sake of fairness. So Modin is the only distributed system that's capable of handling all Dataframe operations. And this is mostly because we derived a theoretical basis for the implementation and actually implemented a new system from scratch. I want to talk a little bit about performance also. So this is run on New York City taxi data, 100 million rows. This is also in log scale. What's important to note here is that this is after several hours of tuning each of these other systems. So by default, neither of these systems could actually run these queries just straight out of the box. If I just imported and then tried to run it, it was not possible in either of these. And for Modin, I did do that. For Modin, I did just import it and then not do any tuning. But we see here a difference of about 100x. This is log scale, so this is a difference about 100x in terms of the difference in performance between what Modin can do and, in this case, what Koalas can do. And then there are also things like calculating median for every column, the true median, not an estimation. Here I wanted to highlight that Modin here is 5.6x faster than pandas, but that's because the parallelism is limited by the number of columns, number of numeric columns in the data set. So if you recall the formalism that we kind of talked about a little bit before, we can actually reason about what the optimal and best performance we could possibly get from Modin is. And of course, this operator requires that a full column actually be materialized on a single worker. So we have the formalism. We know kind of how to implement these difficult operators that traditionally distributed systems have kind of ignored or avoided. Another interesting point to make here is that Modin is modular, so any new component that's developed can be incorporated. This means that performance can really only get better. The last thing I kind of want to highlight is the modularity, again, of Modin and bring your own data processor. So we have a native implementation, but Modin has a specification where we can actually incorporate new systems, and new systems can be integrated, and we can just hand computation off to those systems. And we're still exposing the Pandas API or SQL, or we also have a spreadsheet API. But in this light, we have worked with Intel to actually create a proof of concept on OmniSciDB, which is a very high performance JIT compiled database. And we can actually compile Modin's DSL, Modin's internal algebra, to Apache Calcite, and then hand off computation to OmniSciDB to perform the subset of operations that OmniSciDB can. Again, there's a difference between a relational database and a data frame, so OmniSciDB cannot do everything, but what it can do, it does extremely quickly. And I would implore you, if you have a data processing system that you want to expose that you wish would expose the Pandas API, please come by, the GitHub or our discourse and let us know. We're always happy to discuss. So with that, I'd like to say thank you for attending my talk. Modin's open source. It's always been open source, and it's easy to install with pip. We've generated a large amount of community support and community interest. I'm very thankful to everybody who's been involved. It's been wonderful, and so if you're not involved and you're interested, you want to collaborate. We have lots of collaborators, lots of users. Please, feel free to email me or email the developer mailing list. We're always happy to chat.